But these are the sorts of things that hopefully you should be already familiar with, what you would notice about a graph. One of the ideas, shifting curves, shifting them up, shifting them down, all relied on knowing what the basic curve looked like. So you could look at the equation and go, oh, I know that's going to be a parabola, or I know that's going to be a circle, or you know the basic shape. So the most basic shape, of course, straight line, y equals x, I guess would be the most basic of the basic straight lines. But yeah, both pronumerals basically to the power of 1 there. Parabolas, of course, are our quadratics. So y equals x squared being the basic one that we shift around. So 1 pronumeral to the power of 1, 1 will be to the power of 2. If it was y squared equals x, then it would be on its side. So the general parabola, of course, ax squared plus bx plus c. And when it's in that form, we can tell lots of things from axis of symmetry and all that sort of stuff. Cubics, basic ones, y equals x cubed. So 1 to the power of 1, 1 to the power of 3. The general cubic, ax cubed, bx squared, cx plus d. Now, of course, not all cubics have that inflecting shape like the basic one, right? Remember, those ones, the basic shape, are ones they're the perfect cubes, the ones that can be factorised as something all cubed. Otherwise, it'll be the ones with 2 turning points, the ones that go up and down, or vice versa. And then just polynomials in general. We've done a whole topic on polynomials. Hyperbolas, so when we started looking at asymptotes, so y equals 1 on x, or rearranging it, xy equals 1, so how would you recognise that? You got a fraction, and one of the pronumerals is in the bottom, which is going to create a vertical asymptote. Or if it's rearranged, you notice the x and y is multiplied together, so that might be some sort of hyperbolic function. Exponential curve. That one's easy because the pronumeral's in the power, hence the name, because another name for power is, of course, exponent. So pronumeral's in the power. Circles, x squared plus y squared is the radius squared. So in this case, the coefficients of the x squared and the y squared are the same. And obviously they're both to the power of 2 there. But then we moved on to ellipses, where now the coefficients not necessarily the same. But they're both going to be the same sign, of course, for an ellipse. If the signs were different, then of course that's our hyperbola on its side, the x squared minus y squared idea. Logarithmic curves, well, you see the word log. That's the bit of the giveaway with that one. Trig functions, of course, so we have our sine, our cosine, our tan. And inverse trig was probably the last of all the different types of functions we looked at, wasn't it? So inverse sine, inverse cos, inverse tan. So all those basic shapes we should be familiar with. Other ideas. Symmetry helps us draw. So if we notice it's an odd or an even function, then we know what sort of symmetry it has. Even function having the reflectional symmetry in the y-axis, odd function having the rotational symmetry at the origin. Odd, remember the formal definition, if they ask you to prove it, function negative x is negative function x, and even function negative x is equal to function x. Symmetry in the line y equals x. Now we did talk about this, but it might have escaped you at the time. This was back when we were talking about inverse functions. And we said, remember, an inverse is a reflection in the line y equals x, and how we found the inverse function was swapping the x and the y values around. But what we said was, if we end up with the same function, then that must be reflected in the line. Right? So, in other words, if you've got a curve, well, take the circle. I mean, it reflects everywhere, of course. But x squared plus y squared is equal to r squared. You swap the x and the y's around, it doesn't change the function. So if that happens, then you're going to have a shape that's symmetric in the line y equals x. Okay? So if you swap the x and the y's around and it doesn't change the function, then you've got something that's symmetric in y equals x. Hyperbola is another one. Y equals 1 on x. If you swap x and y around, you get x equals 1 on y, but that can be rearranged to get back to y equals 1 on x. And if you look at your basic hyperbola, yeah, that's symmetric in y equals x. X cubed plus y cubed equals 1 would be another curve that would be swap the x and the y's around, we get the same. So whatever that happens to look like, that would be symmetrical around y equals x. So, as I say, it means the curve is its own inverse. Dominance. is an idea that can help when we're trying to find out what's the curve doing out at its extremities, what's happening as we're approaching infinity. Now, the general idea is looking for which term's going to dominate in the function. So as x gets large. Now, if you're in a polynomial, the leading term will always dominate. That's why one of the ideas when we were doing sketching with polynomials, we said, how does that first term, the highest power, where it starts and finishes, that's where this curve will start and finish. Remember that idea? We looked at that, whatever the leading term was. Well, that's because of this. The leading term will dominate because it's to the highest power. So when you sub into that, we're talking really, really big numbers here. It's going to be so large or so small that the other terms are going to be insignificant compared to it. So in this case, x to the power of 4 would dominate, so we know that curve would start up at the top of the second quadrant and finish at the top of the first quadrant. Exponentials. When you've got things multiplied together, the exponential will dominate, because if you think of your exponential graph, it rises very rapidly. So if you start talking about at infinity, it's now extremely steep and extremely high. So in general, as I say, look for which function would be the steepest. The steepest curve will dominate. And so that will generally tell you what's happening out at the extremities of the function. And of course, don't forget the most basic idea, substitute numbers in. Yeah. Okay, back in year 7, you drew up a little table of values and plotted numbers in. You don't have to do that. But you just get your calculator and sub in a big number and see what's happening. Is it approaching a particular value, or is it getting bigger and bigger and bigger? And often if it's approaching a particular value, it's probably going to be 0 or a lot of the time, but it might be 1 or it might be something else. But sub in a big number. If you're still not sure, sub in a bigger number. Sub in a bigger number. So you might start with 100, then 1,000, then 10,000, and you get a feel for what's happening as it's getting bigger. Asymptotes. Vertical asymptotes, remember, bottom of the fraction can't equal 0. Horizontal and oblique asymptotes. Well, when you do your polynomial ones, or it doesn't have to be a polynomial, of course, but if the top of the fraction is a constant, then the fraction can't equal 0, and so therefore you're going to get a horizontal or an oblique asymptote, because if you've got something plus that fraction, we're saying, well, the fraction can't equal 0, so I can never get this plus the fraction. If you've got the fraction by itself, then it must be the x-axis, because you're saying I can never get 0 plus the fraction. So if you do have a situation with a polynomial that the order of the numerator is greater than or equal to the order of the denominator, do your polynomial division first. You are allowed to cut horizontal or oblique asymptotes, remember? That's just telling you what happens out at the extremities again. So if it cuts it not at the extremity, and the reality is every number is not near the extremity because you can never reach infinity. So it might be at 10,000, but 10,000 is still closer to 0 than infinity. Not that you'd ever create a graph where it cuts at 10,000, I doubt that very much. So just check if you're unsure. Solve the simultaneous equation. The special limit. Often people forget about this one. Remember that special limit? The limit as x approaches 0, sine x on x equals 1. Actually, was it last year or the year before in the extension 2? It was a multiple choice question which simply said, what's the graph of y equals sine x on x? Or something like that. And had 4 choices. And it relied on remembering, well, I know it goes to 1, and so you look at them all, that one's going off to infinity, can't be that one, and so on. So some of those harder graphs too, it could be handy. Okay. Then, of course, we looked at this whole topic of calculus. That was, I guess, the whole point of the course, a calculus-based course. It allowed us to find features of graphs. Okay. So, whilst this topic, it used to be called curve sketching without calculus. Right? So, most of these graphs, we don't use calculus. We just look at it and look for different ideas on how to put the graph together. However, that doesn't mean we ignore calculus. If we're unsure about idea, we can use it to help us find key ideas, critical points, stationary points, inflections, things like that. So what was a critical point? Remember, that was when the derivative was undefined. It's actually when the derivative is undefined or equal to 0. They're both critical points. But because we call the ones that equal 0 stationary points, we tend to think of the ones where the dy dx is undefined as a critical point. Stationary points are still critical points though. So if they said to you, what are the critical points? It would be the ones where the derivative is undefined, but also stationary points as well. They're critical points. The ones I'm interested in are the ones that are undefined. What's going to happen at that point? We're going to get a vertical tangent. If you think what we're saying is dy dx is undefined, you know how sometimes we think about undefined as 1 on 0? So we're saying vertical rise over horizontal run is 1 on 0. So we're going up for every 0 we go across. You end up with a vertical tangent, an undefined slope. The stationary points are the other critical points, of course. We're quite familiar with those, I would hope, when the first derivative is equal to 0. Maximum points, minimum points, points of inflection, because you could have a horizontal point of inflection. And so speaking of those, that's when we can use our second derivative to test, and that then comes down to concavity. If it's concave up and stationary, then we must have a minimum turning point. The other way around, concave down stationary, we must have a maximum turning point. If the second derivative is hard to find, then don't use it. Just look at the first derivative. What's happening either side of that stationary point? Is it going positive, negative, or negative, positive? That can save time if it is a difficult one to find the second derivative. Inflection points, you could use the third derivative test. Or again, if it's going to be difficult and time-consuming to find, test either side of the second derivative. Because an inflection point is a change in concavity. So again, you're looking for that change from positive to negative, but now with the second derivative. But if you do use the third derivative, the key idea is the third derivative does not equal 0, because what you're saying is the rate of change of the second derivative does not equal 0. Therefore, it has a value. Therefore, there must be a change in concavity. So that's an inflection point. Again, as I say, you could test either side. If you get all of them combined together, you get a stationary point and an inflection point. Then, as I say, that's what we call a horizontal point of inflection, the most classic one being the cubic out at the origin. Okay, is the curve increasing or decreasing? The first derivative tells you that, because if you've got a tangent which is positive, the curve must be going up. And if you've got a tangent which is negative, the curve must be going down. So again, if you're unsure what's the curve doing, you can have a look at the derivative to see whether it's going up or whether it's going down. So a positive derivative will be increasing, negative derivative, curve will be going down, decreasing. The idea of implicit differentiation. If you get a curve, it might be hard to make y the subject. Well, that's where we can use implicit differentiation. It might mean to find the stationary point that you need to solve something that involves x and y rather than just x. Or to find the slope of a curve, you might have to substitute in the x and the y value rather than just x value, but that's fine. So let's go back to this x cubed plus y cubed equals 1. Let's see what it looks like. Okay, we know the symmetry y equals x. We talked about that. X and y swap around. It doesn't change. So let's draw that. Okay. X and y intercepts easy enough to find. I know it goes through 1, 0 and 0, 1. Remember, it is its own inverse, so the x and the y's change around. So if I know 1, 0 is a point, 0, 1 must also be a point. Also because of the symmetry. So there's 1 and 1. I know it goes through those 2 points. Okay. It'll have an asymptote at the line y equals negative x. Now this might not be immediately obvious. Let me show you how I work that one out. If I rearrange the curve, I could rewrite it as y cubed equals 1 minus x cubed. Therefore, because I'm always saying 1 minus x cubed, I could never get x minus x cubed. Because I'm always adding 1 to x cubed. So y cubed will never equal x cubed, because it'll always be 1 more. So y equals negative x becomes an asymptote. So that one's not immediately obvious when you look at that curve. So I'll draw that one in. I know that's going to be an asymptote. Differentiating, I end up with, there it is, minus x squared on y squared. That tells me a few things. Y squared on the bottom, so I know when y equals 0, the derivative is undefined. I know when x equals 0, I've got a stationary point. It's also always going to be negative, because I've got minus x squared on y squared. So the derivative is always negative. This curve's always going down. It's always decreasing in value. So except at 1, 0, there's our critical point, and 0, 1, our horizontal point of inflection, it turns out to be. All right, let's draw it. Whoop. That's what it ends up looking like. Okay? Now, there's the horizontal point of inflection. That also tells me why that should be a critical point. So it was a reflection in y equals x. So if that tangent's horizontal, over here it must be vertical. And so on. So there's x cubed plus y cubed is equal to 1. Okay.